Hello. Good afternoon. It's our privilege to have Professor Dipankar Banerjee as a public lecture speaker. Professor Banerjee is a pioneering figure in the topic of solar field. He is engaged in searching the origin of different physical activities happening in and around the sun since last maybe 30 years or so. So he got his MSc degree from Calcutta University in 1989. I was appearing for my plus 10 exam that time. And then he got his PhD degree from IIA Bangalore in 1996. Spent a couple of years in UK and Belgium. He returned back to his alma mater in 2004 as assistant professor. Spent, I think, more than a decade, more than 1.5 decades. Joined in Addis as a director. Spent about 5 years or so. Now he is serving IIST, Indian Institute of Space Science and Technology, as a director. And today's platform, his platform, he will speak about the probing our nearest star from Aditya-L1 observatory. To remind you, he played a significant role in shaping up the Aditya-L1 mission. And he hosts very responsible positions while making these indigenous satellites to be in space in many ways. So without spending much of a time, let's welcome Professor Banerjee and enlighten us about his knowledge and contributions. Professor Banerjee, floor is yours.
Mic on before. Can turn off this now, probably. Yeah. Thank you very much for this kind introduction. And I'm really happy to be here. Stay away from my the speakers. I know. Okay, so it's a great pleasure for me to be here. Actually, there is also a Aditya-L1 supports and workshop, which is a 3-day event which is happening. And we thought that it would be a good forum for me to also report about this mission to some of the Adithians. So very happy to see people from Guwahati. We also have some of the participants who are attending this workshop. So I'm going to give an overview of this mission and the context of why we needed this mission to study the sun, the importance of the solar physics, and we try to review. But then, before I go into Aditya-L1, my talk, I will take this opportunity to advertise also for my current institution for Space Science and Technology, because I understand not many people are actually aware about this institute. Because primarily this institute was actually built for the purpose of ISRO's scientific and engineering requirement. So the undergraduate program with which IISc started its avenue was absorbing 100% pass out research centers. So that's how we have about 340 scientists and engineers in different research centers. They're all IISc pass outs. And they were all taking from the same between what you take, IIT advanced. But then with time, we also have several EdTech programs, and currently we have 200 regular PhD students and 200, sponsored PhD students, because these are scientists primarily working in different research centers as well. So we have 400 odd PhD students. So now, near future, we are going to engage ourselves more into space science research than only technology involvement. Also because of the fact that there is a new space policy through which there are 150 odd companies have registered, formally registered. So our space science students have now possibility of learning many more places, just not ISRO alone. There are complete privatization in terms of satellite building, satellite launching, using the network, 5G, you name it. So the space is going to be completely privatized as in the US. So it's essentially the same format with which the space is going to be operated in India. So that completely translates ISRO's and IISc's role or objective. So we want to be a more research institute and also with the multidisciplinary approach, because that is what the industry also demands. So I want to highlight, we have primarily these two engineering departments, which you can say most of these people have been absorbed in ISRO. We have engineering department very similar to what you have here, and we have several intake. We also have a dual degree program. This is an interesting program that with the dual degree, you can actually choose as many as your solid project something in the master, and then you can go for higher studies and all. And of course, we have several PhD programs as well, and that's the current number strength what we have now. I also thought I will highlight the intake programs that we have, because I am in IIT Guwahati. So that way it becomes, a lot of students are here, those who are interested to go for higher studies. So there are very specific, areas where you can do MPhil. So the entry point is, as you know, GATE, qualifications are only required. So we have many branches, specializations in MPhil. If it attracts some of the IIT students, please, share this information with your colleagues as well. And the other point I want to highlight again is this multidisciplinary nature of the institute, and we are of course involved with major missions like what we call it AI missions, quantum missions, even sensor development, 5G, 6G. There are several sectors in the government has already recognized. So you can find ISD as one such member also in that. So depending on the interest, you can choose to pursue your research either in the master's or in the PhD in these domains at ISD. So this is particularly for IIT students. So, and this is again a very, very representative example how ISD training is more experiential and more futuristic. We have our own ground stations. Our students, undergraduate students, actually build payloads. Every 6 months, we have almost a standard opportunity to fly our payload with a co-emission. I know that you are aware, these are technology demonstration platforms for ISRO, and we get some space in that. Every 6 months, we get this opportunity. Our students build this payload. Sometimes these payloads are also built with international collaboration. So this is an X-ray payload. Why I put up this? Some of the students are working on X-ray spectrometers from Aditya. So this is the same X-ray flux, which is observed from this payload, which is built in actually Boulder, Colorado, primarily to start with, but that was all assembled in our lab at Trivandrum. And that particular payload is actually operated from our own ground station. So our students download the data and they work on the data. So there's another student who was actually working this project, now is doing PhD in the University of Both. So that kind of translation is also possible from ISD. So I think this kind of opportunities are not there in many institutions, even in India. I tell you, this is one of its kind in space institute of this kind of capabilities, one only in this part of the globe. Other very interesting thing I must point out, and I was amazed that how good our entry ISD students have actually to different research centers, because we know research centers are not really accessible that easily. The liquid propulsion lab is just next door. The BSSC, most of the development of whatever happens in Trivandrum is there. The launch station is even the rocket launch is happening. So our students really can get involved with majority of the future missions also. You are talking about man-made mission, our students are actually already involved in the ground. So that's how our students get benefited being part of IST. So that's all about IST development. Let me now move to today's primary talk. Is our son, our new star. This star is actually a very good star. In fact, often we think that the sun is always there and it comes out, it creates and such, but it has certain very of different time scale. This is the one time scale which I have shown here. Namely, we are looking at an image taken from a NASA satellite called Solar Dynamic Observatory, a region of the solar atmosphere which looks obviously much brighter than the surrounding, and these regions are called heat regions because there are lots of presence of magnetic field underneath these active region, and because of the presence of the magnetic field, the plasma material is actually confined in these kind of formation of the loops. But because of certain instabilities, these huge structures can become unstable and can lead to these kind of explosions. We call it solar flares, and eventually a huge amount of coronal material is ejected out of the sun. We call it coronal mass ejection. So these also lead to solar storms, and these solar storms, how it is influencing the interplanetary space and our near-Earth environment, I will demonstrate that. So that's one of the major scientific objectives of our mission. Apart from that, of course, this is our star, being in physics, as you heard. I hope you are working in astronomy after the professional masters. We always look at it as an ideal astrophysical laboratory, whether we call it particle physics, plasma physics, quantum matter physics, nuclear physics, spectroscopy. I can lecture you full day for each topic, how sun can be influenced or used for that. So again, there is another movie which is showing these huge structures when they become unstable, and then these material is ejected into interplanetary space. Some material goes back. All these regions which are light, you can imagine, they are confined plasma regions, and that's why they are much hotter than the other neighborhoods, and they are at the millions of Kelvin temperature, which is again a very mysterious issue. Why is that some atmospheric structures in the high up in the atmosphere, several thousand kilometers off the surface of the sun, is so hot? The so-called coronal heating problem. Aditya also has one of the scientific objectives to explain those, heating mechanisms. So here again, I'm seeing now on a slightly larger field of view of this entire sun. You see this eruption happens from here, but then ejecta goes out. So now we have to track that ejecta at these levels. So to do that, what we do is we block the solar burst by artificially blocking, and this instrument is called coronagraph. This is nothing but almost mimicking total solar eclipse. During the total solar eclipse, what happens is moon comes between us and the sun, and the shadow of the moon, wherever it falls, we have to be in those regions to be able to see the outer atmosphere of the sun in the corona. So here, these artificial eclipses are like a blocking that solar light and seeing the outer atmosphere. We call it coronagraph instrument. So our mission also has such a coronagraph. So that's one kind of very good series I was talking about. So what? Daily for few days to hours. These kind of storms. But then there is another kind of variability in the sun, which is actually very much important for our health. What is plotted here is yearly sunspot number for last 400 years. So I mentioned that those active regions are the regions where there are sunspots. So sunspots are these regions on the surface of the sun, seen for the last 400 years. That is one Galileo, and he counted, how many such small little spots are there on each day. Thereby, you can build a time series, and if you look at that time series, you will find that the sunspot number often is very high, or even very high, as recent knowledge goes. And there are times when sunspot numbers are almost zero. There's hardly any sunspots. These time periods are called solar maxima. These are called, minima. And typically the periodicity is 11 years. But you can clearly see this is not a very simple sinusoidal, curve here. If you would have been a pure sinusoidal curve, it could be very easily explained and predict, how the sunspot number will be for the future. Because these are the periods when there are many more sunspots. Of course, that's the highest magnetic activity means many more storms, many more flares, many more coronal mass ejection, much more trouble in our into space. So we need to understand these variabilities. Why is it that the sun showed this kind of leveling at university? Also, we need to understand if you go back to 1650 to 1700 years, there was hardly any sunspot for almost 50 years. What was the effect of not having sunspot? The water level was frozen for 40 years. People in the place were actually being staying, in England. Several thousands of people actually died in Europe because of extreme cold conditions. So that actually corresponds to the mini ice age. If you go back to the mini ice age, there are many such mini ice ages. So now we understand the mini ice ages were definitely related to the magnetic activity of the sun. So of course you can see that if these ice ages are extended for many years, our technology, our life, everything will change completely. So that means our climate is heavily governed by the radiation which is coming from the sun. And whether there is a magnetic field or not, can also be modulating the radiation output from the sun, which normally nobody actually understands or even aware of. All climate modelers, the first thing they do is the solar luminosity, we call it, the energy coming from the sun to be constant. No atmospheric models actually take any variations of solar radiation output as a very good quantity. Because normally this minimum maximum, the changes in the total energy flux is 0.01%, not really much. But if it is more than that, like this period, this will have a huge effect on our planet. So we need to understand this in a longer time scale. So I just wrote this plot to highlight how important to study the solar variability. Shorter time scale, which directly impacting our day-to-day communications and all that, and talk about it. And the other voice is the long-term variations, which can really change our presence or absence of humans in the earth. So the sun god, is definitely one of the most interesting aspects in the astrophysical scenario also to be focusing on. Now we take a very strong, fast variability of transits, what we call it. This is a movie taken from Partners of the PROF. This is one of the latest, NASA missions, and really the highest technology demonstrations that how close we can travel with the sun. We have traveled actually almost 70% of the distance between the sun and the Earth. We have only traveled 1% distance, be aware, in our own Aditya-L1 mission. So that's the kind of capability we have now achieved in India. Be aware that we are still with many more technological advancement. And you can see the neighborhood of this, region, how dangerous it could be. I mean, if a satellite travels in that neighborhood, or any, in fact, if there's a comet, it will be disrupted. If the tails of the comets are seen to be disrupted by these kind of coronal mass ejection. So we call it coronal mass ejection. So the environment is not very friendly. So to track these coronal mass ejections as it comes from the sun all the way through the interplanetary space and reaches Earth or other planetary atmosphere is very, very important. Even this seems impact the moon. This is the reason why actually life is almost not possible to make the planet except Earth, because Earth has its own magnetic field. We are protected because the Earth's magnetic field provides a complete cocoon or a shield for these high energy particles and material that is coming from the sun. So today, if we are flying a satellite beyond this Earth magnetic field, then they are getting exposed to these these particles and this bombardment. So these solar storms are directly impacting our space assets. So I will talk about we have many more space assets now. It's just not the satellite level. So that's the area we call it space weather. Like our terrestrial weather prediction, it is becoming very, very important to predict the space weather conditions. We are all very much, dependent on atmospheric conditions because our communication systems, this transmission, the satellite transmission, all that is affected by disturbances in the atmosphere. We have astronauts safety. If an astronaut is doing some work outside the space station and there's a solar storm, you can imagine what will happen with that astronaut. There are satellites which are launched, and then they have to go through this, medium. Now, if the storm comes, then immediately also think about this atmosphere is going to get disturbed. So the drag force, which normally we will experience when we travel to empty space, is going to be completely different, and that's what exactly happened just 1.5 years back. Started, correct, launched around 41 satellites. And he ignored the solar storm. It was not a very, very big storm. It happened a few days back, but that changed the environment so much, the electron density content in the neighborhood so much, that the drag, what was calculated for calculating the trajectory of the satellite, was very different. And the satellites could never reach 400,000 kilometers height, which was intended to. They all ended up because of that strong drag back to 200 kilometers and they were destroyed. So he just lost 39 satellites, 500 million for it. But subsequently, that is, all the space companies are now really taking this space weather prediction as a very serious, matter. We are so much dependent on GPS for systems, right? GPS is also used for not only navigation, the drilling of different oil and other components. So they depend on very precise GPS measurement. So if the GPS satellites get affected, then also those gets directly affected. We have lots of power stations, electric power system stations. If high density particles come from the solar storm, they impact the transformers, they destroy the transformers as well. This is precisely happening in a very big solar event almost a day back at Canada. And Tibet was in complete blackout for more than 10 hours. It was a heavy winter, the metros were stopped, the heating system got failed, and people were into getting disaster, thing. People were not taking the space weather as a very serious day-to-day problem. It was more of the solar systems, the one fancy science, so why you find them and all that. But now things have completely changed. In the Western world, the space weather is actually being funded by defense. Well, no, because the navigation system, the defense needs precise measurements from space. Space assets need to be protected by defense. So there are just not NASA who is involved with now space weather. There is UK Meteorology Department who is funding the space weather. It's NOAA, Atmospheric Science, Department of the US is funding space weather. So space weather has become a really, minimum requirement for protecting the space assets. So we are fortunate that fund is not a huge problem now if you are doing space weather. But with the name of the space weather, you also study space weather. Essentially, what I'm saying, see, the weather forecasting is only possible if you understand the source. Right? After all, what is happening in the sun or the solar atmosphere, these big explosions are because of sudden magnetic instability or magnetic connection and these kind of processes. So to understand these processes, we need actually understanding of the physics of it. So that needs, of course, support. The computer is configuration, AI, machine learning for predictions. So that is actually a mutually beneficial now system that looks like. The overall ecosystem of space weather research is quite satisfying because the people who are interested in physics solve it hardware simulation problems on the physical domain are also able to contribute to an application. Because space weather is an application science. But to improve the application, we need, basic science understand. So this is again my general appreciation about our field, that how well, the scientific development in the core branches are important to improve the application. Your applications or your prediction will not actually improve unless you continuously changing your physical models, which are actually used for it. So this is another message I want to carry. Here I will move into architecture. What I have covered here is solar cycle. It almost excludes solar cycle. Chandra was usually for my health year, 50 years, but at least 20 years for the concept of Aditya. And it really coincided very well. I came back in the year 2004, and of course, the presentation we had with the space function was around 2005. So this took a while. Initially, we were given a lower orbit mission, lower orbit single payload coronagraph mission, 2006. Imaging coronagraph with the lower orbit, all the funding and all that was given. We were starting design and project proposals. But there's something happened in between. We had a successful Mangala mission. And after the successful Mangala mission, ISRO people came back to us and suddenly said, well, we'd like to go little farther, because ISRO is now interested to take more challenging tasks. Lower orbit is maybe scale now. So we didn't almost believe, and Professor Yuvala, again, the visionary of space science in India, he came back to us and he said, we can give you a L1. It couldn't believe our, it's a completely contrary to what happens in the Western world, to be honest. People fight for payload mission. ISRO gives us mission. And they said, you can take many more payloads. I said, how, that's the appropriate account. For a single payload mission, it was converted with 7 payload full plate observatory class mission. And again, this is something we could do before the Chinese did. It's only the Europeans and the Americans have reached L1 before us. So that's again the nation's pride. Of course, we had the COVID challenge to build this instrument. Directly were closed, items were not available, all the global tendering was a big problem. Eventually, the payloads were developed and delivered to ISRO in September, in January, to February, March, and then launched in September. This is again the time scale and visibility to the Western world, actually. Typically, you need to hand over the payload at least 1.5 years before the launch in the Western world. But we have no manpower. And interestingly, we were only just after the Chandrayaan success landing. 2 weeks after the success, the entire team was involved with Chandrayaan. And of course, how it can manage, I just don't know. It's really been, 24/7, 365 days, people are really working hard to achieve this. And finally, we have the launch in September. This is a movie of the launch. I will play it for your purpose.
These are visuals from the clean room of the spacecraft preparation facility. This is the Aditya-L1 spacecraft being prepared and ensconced into a protected container where the environment is controlled and the temperature is controlled, the cleanliness is controlled. At the vehicle assembly building area, there is a clean room provision to safely integrate it to the rocket, and then the heat shields are closed. Now the vehicle is fully ready to be moved to the launch pad, which is about 900 meters away. This is PSL mission intends to place the spacecraft in 235 by 19,500 kilometers orbit with an inclination of 90.1 degrees. The total mission duration
Aditya-L1, Surya 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Yeah, all these different phases were out.
Ma'am, this is with top PSLC 57 with Aditya-L1 on board.
That's 50 seconds. PSLC 57 2000 और इसके साथ तथा भारतीय सौर अंतरिक्ष यान निकल चुका है सूर्य के तेज से विज्ञान को प्रकाश करने के साथ ही रिकॉर्ड बने हुए हैं अंतरिक्ष के सफर में भारत की उपस्थिति सिद्ध करने का आप देख रहे हैं PSLC 57.
Okay, I will run the short part of the movie. We also do a bit of a different way as compared to other, Western world. We do several art-centered orbit transfer before going to the cruise phase. This is the fling, mechanism. So we just use it. Here also, I just wanted to, I will not spend too much time. Where is Lagrange 1 point? Lagrange 1 point is about 1.5 million kilometers away from Earth. It is between the sun and light. It is a favorable location because once you reach L1, the force balance is such that you can be in the fixed elliptical orbit around L1 for a really long period of time. And so here it is also giving demonstrations. There are two other, actually three, ESA and NASA missions or satellite around L1. And this again gives you impression it is not in one place, it's almost like a disability figure for this, force balance. So if somebody has a question, I will explain it more. But, it took us several months. So we launched 2nd September, then around 21st, we left Art Center orbit. Then the cruise phase was launched, and then around December, we were entering into this L1 insertion, and eventually we got into L1. And this precision was really so marvelous that we only needed few seconds for correction. And we have saved so much of it that the life of this application is going to be 10 years or more. Initially, it was only planned for 5 years. We were already told that if our instruments can survive, then the satellite will be there at L1. And as you can imagine, L1 is actually a imaginary form. There's no gravitating body here. So it is even harder than the Mangalyaan. Because in the Mangalyaan or any planetary mission is basically you are getting the gravity of the planet. And then you always get on the planet. So the simulation or the calculation or slowing down and all that is much easier. So this is much harder task. So everyone insertion itself is actually probably the reaching everyone and everyone insertion as far as the ISRO is concerned is already a successful. But now it is our scientists' job to use our scientific errors and maximize the science output from the mission, and that's why we are all here. They get a movie for realization of our errors.
Carry out systematic study of the sun. This is a recognition by Guwahati. BANERJEE studies the solar corona and dynamics of corona mass ejections. The Solar Ultraviolet Imaging Telescope, SVIT, uses solar bliss in near ultraviolet and also measures the solar irradiance variations. The Aditya solar wind particle experiment, aspects, and plasma analysis package for Aditya. Papa payloads study the solar wind and energetic ions, as well as their energy distribution. The solar low energy X-ray spectrometer, SOLEXIS, and the high energy L1 orbiting X-ray spectrometer, HELIOS, study the flares from sun over one energy range. The magnetometer array is intended to measure the interplanetary magnetic field at the L1 point. The science fields of Aditya-L1 foundations developed are different laboratories to country. BELC is developed at the Indian Institute of Astrophysics in Bengaluru, Chief Institute in the University Center for Astronomy and Astrophysics, Pune. Aspects of food at physical research laboratory and the lab. Operated at Space Physics Laboratory, pictures on my space center, Thiruvananthapuram. So Lexus and Helios fails, and you are around satellite center, then you, and magnetically fail, and the laboratory for electro-optic systems, you are SC.
So Aditya-L1 is a food-based observatory class mission, and what we have is a combination of remote sensing instruments and in-situ instruments. When we say remote sensing instrument, what we mean is we are sitting at Lagrange point, and remotely we are looking at the sun through this near UV imager called solar ultraviolet imaging telescope. We have this coronagraph, which is working in the emission line, so visible range. So again, this is another very important aspect of any astronomy mission is to cover the multiple wavelengths. Because when you cover multiple wavelengths, you are able to flow different, atmospheric conditions because the atmosphere has multiple thermal layers and emits some things emitted in X-rays. When you have big flares, then you have lots of energy. So we have two X-ray spectrometers which are looking at the particular black what is coming and also looking at a spectrum which allows us to understand the physical mechanisms of these, of these flares and the heatings and so on. And then we have the in-situ instruments, namely the PAPA and aspects, and the magnetometer, which allows us to measure the magnetic field content of these huge, plasma block or the magnetic cloud that comes out of the sun. So before it reaches us, we get a in-situ, quantitative measure of these particles, properties. So as I pointed out earlier, it has its own magnetic field and it is protecting us from these, highly energetic particles and material which comes in. But before it reaches us, we are at L1, so it allows us to quantify the properties of these ejecta as it travels to us. This is sitting in the top deck, the suit and the BLC instrument, because they're heavier, and different other instruments are actually, hanging on at different locations. So this is how, a coronal mass ejections and associated particles travel, and it provides observations through remote sensing, and it also covers the different wavelengths as I indicated here, and we made comparison also with the international scenario as well, because that's also very important area which we need to work. Just for my friends, because in this particular workshop, the coronagraph data is not being shown much. So just for them, the coronagraph is actually moving too fast. Is here with the multi-slit spectral capabilities, and it is internally occulted coronagraph. We have an issue with the spectral line. We are still, but you can be a little bit of now happy that we are able to get this spectral line signature and very quickly running through this just to get a glimpse of this to our friends who are doing this workshop. If you have some, detailed information required, I'm happy to share with you. So here it is this spectral line which I was referring to, which characterizes the properties of the plasma and different regions of the solar outer atmosphere. And here is a movie which shows how dynamic these spectral lines could be. And this is done by one of our student at Radiance here. And we're trying to characterize or do a good output from here. This is done by again another faculty at IA. So you could see that different structures of millions of plasma, how the raster images are able to detect this. So this is some really new results which are coming. It needs a bit of cleanup, but the students have further discussions. I will be happy to do this. This is a paper which is published in Astrophysical Journal later recently. After a CME which propagated, there were certain effects of sudden density pigment was shown, we call it helium, and that again gives you certain properties of these magnetic clouds as it travels, and this is again a new result which is recently published. This is which is the data used by our students who are working this. It has 11 filters, and then we have this At the start of the movie, it was actually a completely thing for us. Because whether that really with a comma and the door will open or not, it was a really big thing. Because if the door doesn't open in space, you are absolutely gone forever. So that was an instance, even before the L1 insertion, the door was open to allow because it's not in space, nobody can do anything if the door doesn't open. So thankfully everything worked, and we have these images of the sun from the suit instrument. This is called solar ultraviolet emitting telescope. It works in the near UV band, and it has several filters. And as you can see, some of the filters are doing some projects for detecting the sunspots and their sizes and all that. Krishna is handling that. So you can see how a sunspot can be seen from these images, and then you can do some science on them. We are also detecting flares. This is again in preparation. This is actually some of it is another bit, but this is something something that we're asking in the morning. So some of these things very close to the sun in these wavelengths were not available. This is the first time our PAOs are able to detect some of these events. So then these are two X-ray spectrometers, which the data again, some of the students working here, we could detect these big flares from these now spikes, and their sort of height and other parameters to say how strong these flares are. This was also taken from the Helios spectrograph, which is a high energy component of these X-ray flares. Then, very interestingly, between these periods, only within a week, there are so many X-class flares, and the strongest flare which is observed from the sun. And we were so fortunate that it can happen that within 5 years we may not have any X-class flare at all. And since we are now in magnetically the highest field of the solar cycle, and we hopefully thankfully got launched in the right time, we are able to detect so many X-class flares. So there are a lot of possibilities. So this some of the data is being made with very closely worked out with the different spectrometers and different layers. This is the magnetometer data. Again, that is detecting this huge magnetic cloud as it travels through the L1 point. Again, with the same period around May, it was observed. So there are glimpses of these kind of results, which I thought I will show. This is a paper already published. Again, multi-wavelength observation. So what you see here is again, of course, different X-ray fluxes, and then also the near UV observations. So we identify the source where these pairs are happening, the change in the source region, and to that nature of the player, its time evolutions and all that is all there in this particular paper. This is again the first police here in the audience. Is leading one of the projects here as well. This is the Aditya support cell, which is conducting this workshop. It is at Ace. If somebody is interested, I think aware, please scan this QR code. This is lifetime opportunity for people like us to be inside the control center to see the launch. And yeah, the game was busy actually distributing sweets. Here we got our foundation from Kolkata to distribute after the launch. He was well prepared for that. My last couple of minutes, I'd like to highlight how important today is to do science or astronomy with the international collaboration and participation. What it shows here is the number of satellites which is there in space. So there are, of course, some which are still to be launched, some are implemented, some dreams are operation. The blue ones are extended operation. I think initially they are expected to be there for 5 years, but they got the extension and they are there still. So what it appears that the entire international community has been looking at the geographic science for a very long period of time, and we have been slightly sleeping for a while. But we are happy that we started with the bank, and we have done a mission which is an observatory class mission, and we are in the neighborhood of these big missions, which are $1 billion. Even so was launched In 1995, it cost us $1 billion. So today, you can imagine how expensive it will be to build another snowball. So we are fortunate for India to be living there. So there is again new satellite which is launched few weeks back. Part of that mission, which is looking at slightly outer portion of the sun. Aditya's finger is only this, and then Punch finger is a big circle. I just wanted to highlight that we are now getting involved with international missions, and observing the sun with a joint observing method is very important. So jointly, with the same kind of understanding, we have to look at the sun, simultaneously, and that is just very important. There is also a mission called Guwahati. This is creating an artificial eclipse in the sun, in the space. There are two satellites. This is called a formation flight experiment, very similar to the FedEx, the docking experiment which India has been doing in space. This is very important for our own space station experiment also, because space station also demands this docking and undocking very, very precise. So all these new stories of Sunita Williams not being able to come back is because of the docking and undocking activity. And now with this new setup with the SpaceX, they could achieve that. And India is already working on that, because we have to have a space station by 2040. So the targets are all set now. We have to land in more by 2035. We will go in space, the several manned missions initially to be, some robots will be sent, then some animals will be sent, and after we are there. Of course, the Russians did it 50 years back, but we are doing it now, because to send the human in the landing moon, these are now required. So PROF was launched in December from, I think, PSLV, from our own rocket. So our rockets are one of the most trusted rockets available in the globe. SpaceX has some reliability. I was told these are first space station, but probably SpaceX was very more expensive also. And they decided to launch from our own satellite. So this is actually a really a highly commendable thing that the international community has come, from institutions like ESA or NASA is actually taking our help. Incidentally, there is a launch from NASA again. There is a project called NISA. You will hear about it. It's again $1 billion project from US, from NASA. We are going to launch it. We have such an instrument which is built in the stack. These are for imaging, remote sensing, but that's again where we are. So thank you for all the attention. This is a picture of Himalayas from our observatory in Davis. It's taken from my Nepal camera actually some time back. So imagine how fortunate we are, how thankful we are. So for the students, we are also enjoying our time by being a poor scientist, or whatever we call it, because it's a very important to enjoy their life. And being a scientist, I got opportunity whatever want to be married in life. Thank you for listening.
Here's hello. It's really fascinating that we heard Dipankar about many unknown facts about Sun, although Sun is our closest star. I'm very, very thankful for his very illuminating presentation. Now the session is open for questions. I think some of the students are around. Please indicate your desire to ask the questions, and they will reach you to take the question.
Yeah, there's one hand here.
Yes.
We'll go. We'll take it next. Don't worry. No, it's there's one here. Yeah. Yeah, that's what. Maybe I will guide. So can you raise your hand and I will probably guide you. Okay. The second one is up there. Yeah, please.
Explain like how the solar cells are created, like the loose how they created.
Okay. Yeah, very good question. So essentially, The solar flares are nothing but, first of all, there are two parts of your question. One, as you said, how these magnetic structures are there in the first place. So, so what happens is there are, we call it magnetic flux tubes inside the sun. And underneath the sun is open. So sun has a convection under the baseline body too. So if you see a magnetic tube